Welcome to Calculus. Today we will investigate evaluating integrals using the fundamental theorem of Calculus 1 for logarithmic and trigonometric functions. Our first example is this definite integral from 1 to 3 of -4 over x dx. To keep in mind the fundamental theorem of calculus, let's give a restatement of it. So just again to recall, fundamental theorem of calculus 1 says that if I have a function f of x that's continuous on the closed interval from a to b, and capital F of x is an antiderivative of lowercase f of x on that same interval from a to b, then the definite integral from a to b of the original function small f of x dx equals the antiderivative evaluated at b minus the antiderivative evaluated at a. So as we look at this example, what we really need to decide is what's the antiderivative for our lowercase f of x here. And when we're looking at lowercase f of x, we're really thinking about the integrand, -4 over x. Well, let's see if we can simplify that integrand and discover for ourselves what that antiderivative is going to be. So one thing I notice is that I have a negative and a constant 4 there in the numerator, and that can pass on the outside of the integral. So my first step is to rewrite this as -4 times the integration from 1 to 3 of simply 1 over x times dx. Now the reason I do that is because that much simplifies this f of x. If we're going to identify this with the fundamental theorem of calculus 1, that's my f of x. So I really need to think, how would I get back to, if this was my function, what would be the original function before I took its derivative? That's kind of the idea behind an antiderivative. So here on the side, I'm really going to think, in fact, that my uppercase f prime at x is going to be 1 over x. So the question is, what's my antiderivative have to be initially if I were going to take its derivative and get 1 over x? So we've got to, in a way, think inversely. We've got to think, in a way, backward. So if you recall, the original function whose derivative was 1 over x is the natural log of x. And so for us, we can apply the fundamental theorem of calculus using this very function, capital F of x equals natural log of x. So we just need to apply that theorem to this specific example. So we'll just pick up right here, -4, and now I'm ready to evaluate once I've identified the antiderivative. I'll place it here within my brackets to evaluate from 1 to 3, and then setting up according to this second-hand side of the fundamental theorem of calculus. This is now simply -4 times the natural log. My upper limit of the integration is going to be 3 minus natural logarithm of the lower limit of integration, 1. And there's a couple ways we could look at this difference of two natural logarithms. The first is that I could collapse this as a quotient. It could be the natural logarithm of 3 divided by 1, which is going to just reduce to the natural logarithm of 3. Another way to look at it is natural logarithm of 1 is really saying e to what power would give me 1, and that's 0. So this would also just reduce to 0, which would just leave natural logarithm of 3. Either way we look at it, we're going to get -4 times natural log 3. And again, just to emphasize that this is a definite number, we could plug this into a calculator and get a decimal approximation. And I've done that already. So that's going to give us a value of about -4.394. So definitely for an integrand that's set up as a rational function, we can really find our antiderivatives as the natural logarithm of x. Let's take a look at a second example of the definite integral from -1 to 0 of -3 times e to the power of x. Again, we want to think in terms of the integrand and its antiderivative. So I do see that I have a -3 constant that can pass to the left outside the integration. So this would be equivalent to -3 times the integration from -1 to 0 of simply e to the x dx. So that's very simply identified then as our f of x here is e to the power of x. So I'm really looking for the antiderivative of e to the power of x. So I'm asking myself, what would the original function have been to have its derivative equal e to the power of x? Well, we don't have to look far. That original function is simply e to the power of x. Recall that it's its own derivative. So applying FTC1, Fundamental Theorem of Calculus 1, it's also its own integral, or its own antiderivative. Well, let's again apply it. So now we can say that this is equivalent to -3 times the antiderivative e to the power of x, evaluated from -1 to 0. That gives us opportunity to evaluate. So according to the theorem, it's going to be e to the power of the upper limit, 0, minus e to the power of the lower limit, -1. We just saw this within the natural logarithm. Logarithm of 1 was 0. Another way of looking at that is e to the power of 0 is 1. So as we simplify, this is going to become -3 times 1 minus e to the power of -1 is going to be 1 over e to the power of +1. And then if I distribute the -3, I'm going to get -3 plus 1 over e. I see I've made an error there. Forgot to distribute the 3 correctly. Let me correct that before we get any farther. I do need that numerator to be 3. So -3 plus 3 over e. Again, I can get just a decimal approximation. That would evaluate to about -1.896. So a good view on e to the power of x is that, as we saw with differentiation, it is its own derivative. Well, according to the Fundamental Theorem of Calculus 1, it's also its own integral, or antiderivative. Let's take a look at a couple examples that are trigonometric. Here I've got the definite integral from 0 to pi over 6 of -2 cosine x dx. So we're getting used to bringing these coefficients outside of the integration. We'll do so here as well. So -2 is going to pass to the left, times the definite integral from 0 to pi over 6 of simply cosine x dx. So I've identified that inner function, small f of x, to be cosine of x. So as I look for my antiderivative, I'm going to think, what was the original function that would have had the derivative cosine of x? And recall that that function was sine of x. The derivative of sine is going to be cosine. So we're ready to apply the theorem. This is now equal to -2 times the antiderivative sine of x, evaluated from 0 to pi over 6. That's set up to evaluate now. -2 times sine of the upper limit of integration, pi over 6, minus sine of the lower limit of integration, 0. And that's going to reduce down to -2. And we can evaluate these two trig identities. Sine of pi over 6. Recall pi over 6 is equivalent to 30 degrees. So that has the value of square root of 3 over 2 and 1 over 2, radius of 1. So that's going to have the value of half. Remember, sine is the vertical element over the radius, minus the value of sine at 0. It's hard to draw that triangle, but it's a flat triangle with 0 height. So the value of sine at 0 is 0. And that's going to reduce down to really -2 times half, or -1. That's an exact answer. Our final example is this definite integral from -3 pi over 4 to -pi over 2 of cosecant x cotangent x dx. With this example, there's nothing to move outside of the integration in terms of a constant coefficient. So we're really just looking at the f of x here as cosecant x cotangent x. So I want to think again in terms of antiderivative. If this derivative is equivalent to cosecant x cotangent of x, I'm thinking to myself, what would have been the original function whose derivative would have been cosecant x cotangent x? And in fact, there is no such original, because we did have something else that had the derivative negative cosecant x cotangent x. If we add that negative in, we can easily find our antiderivative was going to be simply positive cosecant of x. Now, I do need to make a change. So up till now, we haven't had to incorporate anything new into our integrand. I do need that negative sign there. So what I want to do first is I want to double the negative. I'm going to write a -1 on the left side of the integration from -3 pi over 4. So I'm not changing the limits at all to -pi over 2. But what that allows me to do is place a second negative here with the integrand cosecant x cotangent x. And all of a sudden, that's ready for the antiderivative cosecant of x. This doubling of the negative is equivalent to the original positive. So that gives me -1 times the antiderivative cosecant of x, evaluated from the lower limit of integration -3 pi over 4 to the upper limit -pi over 2. And we'll evaluate by plugging in or substituting my limits. Here I've got the cosecant of -pi over 2, the upper limit, minus cosecant -3 pi over 4, the lower limit. And we're ready to evaluate these trig identities for cosecant. So remember, cosecant is the inverse of sine of x. And remember, sine of x is the y component, vertical component, over the radius. So another way of looking at cosecant, if we find the reciprocal of that, is the radius divided by the vertical component. So when I consider, for instance, the angle -pi over 2 on the unit circle, the negative direction's clockwise, and then -pi over 2 would be the -90. And so when I think about the y component there and the radius, they're actually the same number. It's just this is going to be a y component of -1, since it's in the downward direction over the or underneath the radius of 1. So as we evaluate, that's going to give us -1 times -1. And then let's think about the value of cosecant. Ooh, I've got it written as cosine. Let me make sure that that's cosecant at -3 pi over 4. So it is in the negative direction again. So -pi over 4 would be to 45. -2 pi over 4, that's what we saw above at -pi over 2. -3 pi over 4 is right there. It's a version of the 45. So if I think in terms of the y component, it's going to be negative square root of 2 over 2. And my radius again is always 1. So the value of cosecant at negative 3 pi over 4 is going to be 1 over negative square root of 2 over 2. Before we import that over here, I want to clean it up in terms of its presentation. So I can see that if I multiply by the reciprocal of that denominator, that's going to be negative 2 over square root of 2. And that'll cancel everything below. Above, I'm going to multiply by that same factor. And so this is equivalent to negative 2 over square root of 2. And then I need to rationalize that denominator by multiplying by square root of 2 above and below. And that's going to reduce to negative 2 times the square root of 2 over square root of 2 squared is going to be 2, and then I have a final reduction. Those 2's cancel. So it turns out the value of cosecant at negative 3 pi over 4 is the negative square root of 2. And that gives me my last value there, negative square root of 2. So that gives me one last step here. I just need to distribute my negative 1 through my parentheses. And that's going to give me a final answer that's exact of positive 1 minus the square root of 2. And then a good decimal approximation. Remember, square root of 2 is 1.414. So if I'm subtracting 1 minus 1.414, negative 0.414. And that completes the integration of the cosecant x, cotangent x. Thanks for joining for these 4 examples of integrating logarithmic and trigonometric functions using the fundamental theorem of calculus 1. Thanks for joining. See you soon.